In this video, we introduced the concept of a vector valued function, right? So we're gonna, take what we know about functions, take what we know about vectors, smush them together, and create a new thing. And we're gonna see what we can do with this new thing. Before we get into the specifics, however, I do want to say just a bit about, the concept of a function and specifically the types of functions that we would have used prior in prior math courses, like algebra, pre-calc, and so forth, and just say something about the notation, and then take that notation and apply it to what as actually as a way to introduce this concept, right? So, for instance, in your previous math classes, you probably studied equations that looked like this, and we refer to them as functions, and we have this nice function notation, and we have variables. So we have variables y, variables x, and this is just the name of the function. And the y is often used to represent the dependent variable, and the x is often used to represent the independent variable, and so forth. And we know that this this type of equation, depending on what f is, what type of function it is, it will generate different types of graphs and so forth, right? But what's often lacking, unfortunately, in those preparatory courses is the fact that you can't really define a function before you define the domain and what's called the codomain. Basically, when you talk about the domain, the question is, okay, what am I going to put into this function? What is the input? What is my set of inputs? And then what do I hope, right, to get out of this function, right? In other words, the set of outputs. So the formal definition of a function requires, before you get to the equations and all the other stuff that you do, it actually requires a clear definition of your inputs and your outputs. So what's missing is this. So this is incomplete. Here it would be the complete description of this. If I am working, let's say in calculus, and I am working with a function of real numbers, then what I would say is this: f, I still have your name, so f is a function, and that's kind of what this notation in this context is referring to. It's a function such that real numbers, right, represent my input, and then I'm going to take these real numbers, and when I apply this function to these real numbers, well, what do I expect to get out? Well, in our previous classes, we would expect to get out other real numbers, right? And then below, you will say that, okay, f of x does whatever. How do I hope to achieve this? Is it a linear function? Maybe it's something like this, right? And all of this together would be the complete description of the function. So here's another example of how it might be. Maybe I have a function that is only defined on the positive or the non-negative real axis. So like from 0 to infinity. And what I would hope to get out of that, let's say, is, again, real numbers. Whether you get all the real numbers, and that's where you get into domain and so forth, and range. Well, that's a slightly different discussion, which I won't get into. But yeah, you could have something like this. So then my function could be, let's say, the square root of x plus 2, right? So stating your domain is the correct, is the precise way to lead into your function. Let me write one more. Let's say h is the set of, let's go back to all real numbers such that, well, h is a function that will map real numbers onto real numbers. That's how we would say it. And then you can write down what the function does. So it might be something like 1 over x squared plus 1, right? And the idea is when you state the domain first, whatever rule that we come up with, right, has to be well defined for all of the elements in the set, right? So whatever I wrote down here would have to be well defined, right? This expression, right, would have to be well defined for all the elements here, right? So again, these are the types of functions that you'd have worked with in algebra and your first 2 semesters of calculus. Here, when we talk about vector valued functions, so let me say a little bit about what we've done up to this point with these vectors. In addition to all the operations, we've studied lines, right? So, and again, so here's our new form, and this is what we have as far as the vector form of the equation of a line in 3 space, right? And again, based on how we've defined it, our parameter t would have to take on all possible values, right? But the interesting thing now is if we change our perception, right, of the letter t, it's almost like we can think of this function as a function where when you plug a real number in, right, into this, we're not going to get a number out now. We are going to get a vector. So for instance, so let me write down a specific one, right? So for example, if we have this, so let's say here is the vector equation of my line: 1 minus 2t, 4 plus t, 8 minus 7t, something like that, right? Well, if I plug 1 in, right? Oh, so if I use my same notation to say, okay, if I'm going to evaluate this at a specific value of t, so if I plug t equals 1 in, well, I am going to get this vector. It'll be 1 minus 2, which is negative 1, be 4 plus 1, that's 5, and then 8 minus 7, that will be 1. So what I end up getting when I plug 1 into this, vector function, I actually get a vector out, right? So unlike the previous functions where you plug a number in and you get a number out, what we're going to be studying now are functions that when you plug a number in, you're going to get a vector out. And that vector could either be in 2 dimensions or in this case, 3 dimensions. So a vector valued function, so a vector valued function is one whose domain is some subset of real numbers. So again, it could be all real numbers or it might not be, but we're going to start with real numbers. So I'll say whose domain is a subset of R, right? So that's what we're plugging in. We're plugging real numbers, and whose codomain, which is that's the fancy word for the set of outputs, and whose codomain for us is either R2, where we're going to get out 2-dimensional vectors, or R3, where we're going to get out three-dimensional vectors, right? So let me now write it down formally, and you'll see this in much of our subsequent work. So R is going to be a function that accepts real numbers as its as inputs, and then it is going to give us back either vectors in R2 or vectors in R3, right? So the big difference, and it's not just a conceptual difference, but it's also a procedural difference, right? Where instead of working with real numbers in, real numbers out, we're now going to be working with real numbers in and vectors out, either two-dimensional vectors or three-dimensional vectors, right? And we've actually seen one such function. You know, the lines that we were working with, you can see it, that it's of this form. And I just evaluated this one at a specific value of t, just so you could see a number in and then a vector out. And what we're going to be doing over the next few videos is expanding this idea. What if the components aren't linear anymore? What do we end up with, right? So in R2, and just to emphasize that these are going to be functions of t, our vector valued functions will look like this. We'll have some function in our x component and then some function in our y component. And in R3, our vector functions will look like, you'll have, again, an x component, a y component, and now you'll have a z component, right? So this idea of just extending what works in R2 by adding a third component, we can then move to R3. And the question is, what do we make of these? Like, how do we really interpret the idea now of things like, so let me just write down a few examples. So, how would we make sense of something? What if I had like t squared comma 8 plus, the e to the negative t? What if I had something like that? Suddenly, it's certainly not a line, right? It's certainly not a line, but what is it, right? And then similarly, what if we had something like sine of t, cosine of 2t, and like the natural log of t squared plus 1? So all of a sudden, all those functions that we would have, like, let's say, studied in in algebra or calculus, what if those functions are now showing up as components in our vector functions? Well, as I said, what we need to do is to have a clear understanding of what this means. Now, we are going to interpret the function r as a position vector, right? So we're going to interpret r of t as a position vector. And remember what a position vector means. It means that it always has the initial point at the origin. So initial point at the origin. Okay, so that's not up for negotiation, right? That's a given. So then the question is, what would the vector's terminal point be? The terminal point will be determined by the components of this vector after evaluating it at certain values of t, right? So the components And this is true in both 2 and 3 dimensions. So the components represent the terminal point, right? Terminal. So terminal point of R of t. So that gives us a way of actually sketching this. So now I'm not going to sketch this one in particular, but I'm just going to say in general, this is how we're going to interpret it. So again, I'll sketch it in R2 because it's a little bit easier. Right. So we have our, and again, let me use our notation here. So we have some function, right, that takes inputs that are real numbers and gives us vectors in 2D. And I'm just going to call it R of t. And suppose my parameter t, or now we can think of it as our independent variable, ranges from, let's say, from t0 up to, let's say, tn. So there's a range here. Well, what I can do is, let's say I take the smallest possible value of t, or I take some value of t and I plug it into my vector function and I evaluate it just like I did previously. I would plug the value of t here, get a number, plug the value of t here, get a number. Then what I would do, I would plot that vector. So I'd plot the vector, it would be here, and then I'll just plot it dashed like this. And then this would be its terminal point. So this would be the R of t0 vector, right? And then I would do that process repeatedly for several values of t, all the way to, let's say, t sub n. So again, I would pick another value of t, let's say t1, and I would plug it in. Again, I would evaluate all the components of my vector as long as the value of t that I am plugging in is in the domain of each of these. So each of the components would have to be well defined. And then I would get another vector. So let's say I get this vector with that terminal point, and then this is R of t1. And again, continue that process. Let's say I plug another one in and I get this vector. Let's say this is R of t2. And then over here, let's say that this is R of t3. And then I'll just kind of finish it up. And let's say I plot my last, or yeah, the last value of t, and let's say I get this vector here. So this is the vector R of t sub n. And again, each of these vectors, they have to have a well-defined terminal point. So what I could then do, I could say, so this vector produces all these terminal points. If I were now to connect them, like for instance, when you learn how to plot like a parabola, you cannot, the first thing, the way you learn to plot a parabola initially was to take a sampling of x values, plug it into the parabola, get your y values, and then you'd connect those points, to indicate the pattern. Well, let's say I connected all of these points like this, and they end up giving me some nice curve like this. And because I have a well-defined almost order in which these vectors, these R vectors would be produced, right? I could say that it literally would start at this point, and then we would move in this direction along this curve like this. Right? And this, so what I have in green now is what we would actually plot, and we would say that this green curve is the plot of our vector valued function, right? So it's another way of generating curves, but now we're using vectors. So what I have in green is the plot of r of t, right? And r, so and because of this, so r of t can be interpreted as a curve in either the plane, or if we were to do this in 3 dimensions, and it would work exactly the same way in 3 dimensions, this function here would describe a curve in R3. So R of t, right, a vector valued function, right, represents a curve either in R2, right, or R3. In R2, it would be referred to as a planar curve because it's in a plane, right? So in R2, R of t is described as a planar curve. Right? Again, it's another way of describing objects that we have a lot of familiarity with. We know a lot about curves, and we now know a bit about vectors, and we're putting those ideas together. In R3, R of t is described as a spatial curve, or just a space curve. That sounds so cool. So is described as a spatial or simply space curve. So I'll do space curve, right? So again, these are not just things that, okay, we know functions, we know vectors, and we kind of put them together. We have a geometric way of interpreting what these vector valued functions represent. Now, once we are satisfied with this, right? And I don't know about you, but I'm pretty satisfied as now because I'm thinking ahead. But once we're satisfied with this idea now of working with a function where our input is a number and our output is a vector, then we can try to extend all the things we know about functions to this type of function. So what do we know about functions? As I mentioned, we've talked about identifying the domain of a function. We know how to evaluate a function, but then you get into calculus. We know about limits of functions. We know how to differentiate functions. We know how to integrate functions. So can all those operations be extended to these types of functions? And if so, how would we interpret them, right? We have a way of interpreting a derivative of a function of a single variable, right? Y equals f of x. But what would the derivative of a function like this, how would that be interpreted? How would an integral of something like this be interpreted? And those are some of the cool things that are yet to come, right? So I just wanted to kind of use this video to, again, formalize some of the notation that you will see going forward. And you will see variations of this type of notation going forward. And then the idea of having a function now being expressed as a vector and showing you not in a very abstract or even difficult way, but you can see that we can associate something very familiar with that type of vector function or vector equation. All right. So in the next video, I think what I will do is show some actual ones. So I mean, yes, it's all well and good for me to sketch something, but I will show you a couple plots of actual vector valued functions. So why not just hop on over right now and take a look. See you then.